Kaisar, come on up. Kaisar is from Rally Source, and he's a principal software engineer there, and he's going to be talking about nanotechnology. No? Not nanotechnology? No? Okay, probably he's going to talk about the next best thing. It's embedded software development. Alright, his challenges in embedded development, and it's pretty interesting. He's got a pretty good, slides round up. You going to start now? Okay.
Thank you. Okay, so my time starts, right? So we're going to talk about some challenging scenarios in embedded development. It's particularly actually focused at embedded software development because there are two major parts in the embedded world. One is the hardware side, one is the software side. So we'll be talking about the software development side. So first of all, what is embedded? Embedded actually can be a lot of different type of platforms like 8-bit microcontroller units, we call MCUs. 16-bit MCUs, 32-bit MCUs or processors, and any architecture or any device that are like deal with these sort of processors or MCUs are embedded, like our mobile phones. Okay, so the architectures and platforms actually differs in a lot of ways, like costing, physical size, power consumption, etc., etc. And for example, all of the platforms are currently popular. The 8-bit one are not like something that our grandpa uses or very old stuff. Those are coming out every day, and newer models are being in the market every now and then. And these are like two random images, and we are using actually one of these devices in our application that we do at Rally Source. So the first challenge that I'll be talking about is the resource constraint. The resource constraint is actually the most serious case in embedded development, because this is the thing that we have in the embedded world. In an embedded platform. For example, in our home PC or in a server, we have like 2 gigabytes or 4 gigabytes of RAM, and we don't care about how much RAM we have and how much hard drive space we have. But in a platform like the 8-bit MCU, we have this is a typical a scenario where we have 1 kilobyte of RAM only and 16 kilo instructions. We can have the code size in between those 16 kilo instructions. So these are the two serious cases, and we also have limited peripherals. Okay, so talking about constraints of resources, the Vice President of Nokia Research Center says this is what is different from other software development. That is the resource constraint. You have to constrain the everything, like the pixel constraints, the power balance, simplicity, and footprint of the software, etc. So let's see some examples of our like regular software development that we do. Say we have this code. This is some function that what it does, it just simply multiplies, right? So when I ask the developer to write a code like that, a function that will multiply, he'll simply write something like that. But in embedded, we have to be very careful about what we are writing, because the code size that it produces is basically going to have a huge impact. For example, we have long here, the data types are long. These are expensive in terms of the core size and the RAM size, because using long, the assignments can be expensive, and all the operators, the multiplication, it can be expensive. So we have to be careful what we need actually. We can, for example, if we have a limit of 200, in variable A, if we have a limit of 200, and in variable B, if we have a limit of like 100, then we can probably use 8-bit integers. So we can save some code size using the right kind of data type that we need. And even for this function calls are pretty expensive. You know, for every function you write, the compiler generates like 10 or like 12 different steps. Or for every function call, it actually does these 12 different steps where it does a lot of things, like it makes rooms for all those parameters and the return type, and then it jumps into the code, and then when the function call is over, it stores the return type, and then the stack frame is changed, and all these different kind of things. So functions calls are very expensive, so sometimes we need to like use macros instead of functions. So macros are typically good for some scenario, but not in all cases. Like if you have too many macros, it can have impact on your code size. So you have to be careful about what to use, the macros or functions and stuff like that. And some operators are expensive, like this multiplication, and we can replace these operators, expensive operator, with some other operator like a bit shift. For example, y is multiplied by 8. In this case, we can like have a bit shift of 3-bit left shift, and it will have the same result of that multiplication with 8. And the thing is, this sort of careful calculation can save you like 10 or 20 instructions. You know, if x and y are long variables, then it will take like 16 or 24 or something like that number of instructions, depending on the architecture that you use. And for floating point, you have to be really careful about how to use a floating point, because floating point are like ugly and evil, and they take a lot of space. You know, like if you multiply 1.5 into 1.5, this multiplication will take like far more number of lines than 15 into 15 if you consider the integers. So for code size, we need to understand, in an embedded world, we need to understand what each line of your code actually is doing in terms of the machine code that it generates, and how to minimize your code. So, yeah, and for RAM size, you need to really understand what the variable types you're using, how to minimize the RAM utilization. And you need to actually save every bit, not every byte. We sometimes need to consider saving every bit. For example, this is the data type. That one of the examples that I have given. We use long, and using unsigned integers will save. And for saving every bit, this is a very simple example where we have like two variables having a range of 1 to 50 and another variable having a range of 1 to 10. We can actually combine them into a single variable, into a single structure where it will take 1 byte, but it will actually serve your purpose. So we need to consider these cases. We need to use bits and bit fields, and those are things. In embedded world, sleeping is better than working. This is true. So why is that? Because power is a major issue, and when your peripheral or your device is running in a high-speed clock, or like in doing a lot of operation, it utilizes power and actually consumes the battery life. More battery life is more battery life. You need to reduce the battery life and power consumption, and it will reduce the cost and do better for a business, and less batteries and greener world, and these sort of things. So we have a lot of different real-time issues too, like the communication issues that we have. Actually, I had a lot of slides. There are probably too many slides. So these are the things we need to actually consider for embedded development, and I'll just stop here for today. Thank you.
I was so into this, I actually totally lost track of time. We actually overshot the time anyway, but it was really good. It was very interesting. See, nowadays I see that, when programmers are doing their coding and everything, they want to be bleeding edge, cutting edge, jQuery and all those kind of things. It comes up again and again. I want to work with jQuery, I want to work with JavaScript, I want to work with Spring 2 and all those kind of things, stuff. So, but when you're working on this kind of thing, it's totally the opposite. It's not cutting edge or bleeding edge or whatever. It's like Stone Age. It's totally Stone Age. And that's interesting. I mean, do you like doing this? Have you found fun?
Sure. From your point of view, it's like a Stone Age, but from my point of view, it's no, really, it's positively. This is probably the cutting edge, because working with embedded is one of the most challenging things that we do in software development. And because if you look at the challenges that you have and the technology that you're working with, it's the latest thing we're working with. These are the processors, these are the platforms that are not in the market that we're working with. We're working with some feature that we do at RailSource. We're working with some feature microcontrollers or some processors platforms that will be in the market in the next 6 months or so, but we are doing it right now. So these are obviously cutting edge, and And the definition of age or definition of technology, I mean, is there a definition of cutting edge or bleeding edge?
Well, you're absolutely right, and the reason I've asked this question is that you send out a message over here, because a lot of people don't understand this, actually, what I'm saying. People have come out of college and they want to do all this great stuff with the latest .NET that's coming up and everything like that. But over here, you have to worry about bytes, no bits. And it's an 8-bit processor you're working on? It's an 8-bit processor! My watch is probably better than that if it was a digital watch. And it's mind-blowing, I mean, these things. So what would you want to tell them that about cutting edge and bleeding edge?
Okay, so there are actually particular things that are applicable to particular scenario or business problems. Like, if you talk about .NET, you don't run into a 3-volt battery devices, right? So these has particular scenarios where
they'd be excited about it, because it's something to get it. I was excited, that's why you overshot it. When I saw that, it reminded me of my job at.
So the thing is, the basic thing is that all of these technology verticals have their own domain, have their own applications. For example, I can really say this 8-bit platform will will resolve all the needs for .NET or ASP or PHP or Ajax that we do. Actually, all of these have different verticals, different applications. We cannot actually have some .NET code into a machine where it consumes 0.5 milliampere per instructions that it takes. We have a lot of battery requirements. For a simple example, what we can say is these particular devices that we work with cost around less than $1 per unit. These microprocessors. Does your PC that you run on .NET cost less than $1?
What's your salary? Don't answer that. I mean, I'm thinking about the CEO who, tries software for a $1 device. I said, how much should I pay this guy? But, look, I was just kidding. But, I'm excited about this. And question and answers, please.
Yes. And the thing is, about the $1, the platform, we produce 5 million of them every year, so that's a huge number. And the processor itself costs $1, and the whole unit probably costs $3-4, and it's a huge business. So any questions here? Yes, this is some sensitive information, but what I can say is these are temperature monitors or temperature logging units that can take thousands and thousands of temperature of a particular storage or scenario in chemical industry or food industry, any perishable things. And these can actually have some business logics, you can say, I want some alarm triggered when the temperature goes below 20 degrees or goes up 80 degrees Celsius or something. So we can have those business logics in those temperature monitors. So temperature monitors is one of the examples.
In the US, we have a lot of the smart homes, and so I live between, well, now I live in Saudi, but I'm from the US. And so in Saudi, this is coming over, and so I just remember, a lot of developers talking about these smart home, doing embedded systems with smart homes.
Right.
And in Saudi Arabia, they're thinking about the smart grid and those.
Yeah,
they just spend money.
Well, just to give you additional information, this device actually that we work with is the primary product that is sold in this category in the US market, and this is the market leader. And we do it at real source. These are the millions of units that is being produced in the US and used in Walmart and all those chain shops and a lot of different industries. Any other question, please? Thank you.